Okay, let's build on our discussion of momentum and momentum conservation to talk about collisions. So, uh, before we jump into uh, looking at some example questions, we need to define types of collisions. So there are basically two kinds of collisions. There are elastic collisions and inelastic collisions. So an elastic collision, both momentum and kinetic energy are conserved. And in an inelastic collision, only momentum is conserved. And so, of course, in this, let me put this in a different color just to emphasize it. The kinetic energy is not conserved. And this distinction between elastic and inelastic collisions is important because it determines the kinds of math, the equations that we're going to be able to use for solving problems. And I should mention there's one special case of inelastic collisions that we'll work with, and that is something called completely inelastic. And this is the situation where your objects stick together. So kind of the cartoon, that situation is like you have one object and it hits another one, and then you have that combination that sticks together after the collision. So it's one special case. But these are our main definitions: elastic collisions and inelastic collisions. And I should say most collisions are inelastic. Elastic collisions, if you think about the kinds of things that we have seen, so the ballistic pendulum, for example, when you're talking about big objects, macroscopic objects, usually they're going to be inelastic. And most of the kinds of collisions that we see in sort of our everyday experience are going to be inelastic. Elastic collisions, though, could be things like particles, where they don't actually touch and that situation allows for elastic collisions where they conserve energy. So let's look at some examples here. Oh, and I should say this is basically sections. Let's see, 9.4 through 9.6. So let's look at an example. Paste it in here. So we're gonna, after I just told you, most collisions are inelastic, we're gonna start with an elastic collision problem just because we want to look at both cases. But I think what you'll find is sometimes the questions are they come across as sort of contrived. But that's okay. It still gives us an opportunity to practice the math. Okay, so here's the question that I want us to look at. A 1D elastic collision. So imagine, despite this being a macroscopic object, we have a 0.45 kilogram hockey puck moving east with a speed of 4.8 meters per second. It has a head-on collision with a 0.9 kilogram puck initially at rest. Assuming a perfectly elastic collision, what will be the speed and direction of each object after the collision? So, okay. So like I mentioned, this question is perhaps a little bit silly. I don't know why the hockey pucks have two different masses, but this gives us a chance to practice. So let's sort of draw a cartoon here of what's going on. We have a hockey puck that's moving with some initial speed of 4.8 meters per second. Oh, and I should say, this will be a one-dimensional problem. So we're going to look at the one-dimensional case first. And this has a mass of 0.45 kilograms, and it's going to hit this, for whatever reason, more massive puck, 0.9 kilograms. And what we are interested in is we want to know what the speed and direction of each is after the collision. So I think what you will notice when you go to start working problems on momentum conservation is the ideas are often quite simple. We know that the momentum has to be conserved. And in this case, it's an elastic collision. We know that the energy has to be conserved. Those things are easy ideas. However, where it gets difficult is just that the math, the algebra, can get a little more complicated. So part of what I'm going to do is show you this question kind of in all the details. So hopefully that gives you a sense for how to go about solving problems like this. And then I'll show you some tricks so that you can make it easier mathematically. But I don't want to show you those things from the get-go because it can be a little bit confusing as to where those things are coming from. So we'll look at this problem in a couple different ways is basically what I'm saying. Okay, so like I just said, how the algebra can be a little bit complicated. Let's kind of take stock of this problem. So we know MA, we know MB, we know the initial velocity of A. We also actually know that VB initial is 0 because notice it says that this puck is at rest. What else do we know? Well, since this is an elastic collision, we know that both momentum will be conserved and kinetic energy conserved. And what are we looking for? Well, we want to know in this terminology, we want to know what VA prime will be and what VB prime will be. Okay, so let's start by writing down our expressions for both momentum and energy conservation. So let's look at kinetic energy. We know that the kinetic energy initial is going to have to equal the kinetic energy final. That's energy conservation. And what does that mean? Well, 1/2 MVA squared plus 1/2. Oops, I got to be careful here. So we have two different masses floating around. 1/2 MAVA squared plus 1/2 MBVB squared is going to have to equal 1/2 MAVA prime squared plus 1/2 MBVB prime squared. And we know right off the bat that VB is 0, so this piece will be 0. Okay. Let's look at our momentum conservation. So the sum of the initial momentum is going to have to equal the sum of the final momentum. So MA VA plus MB VB is going to have to equal MA VA prime plus MB VB prime. And just like with the kinetic energy, we've been sort of very complete by putting the MBVB term, but we know that that will be 0 because the initial velocity of B is 0. Okay, so basically we have two equations and we have two unknowns. So we can substitute, for example, one into the other to eliminate one of our unknowns and then solve for the other. So, for example, so there are, of course, more than one way to go about this. How about we do this? We're going to solve our second equation for VB prime, and then we'll substitute it into the first to eliminate VB prime. And the reason that we're going to do that is because if we were to solve the first equation, we would have to take a square root. So I think this will be a simpler approach. So, but it's not unique. So from our second equation, notice we can solve for VB prime. We would see that it would be MA VA minus MA VA prime divided by MB. Okay, so we have an expression for VB prime. Let's substitute it into equation 1. Okay, so, and notice we can actually do some simplification. This factor of 1/2 is common to all these pieces, so we could eliminate that. And let's then substitute in for VA prime. So we would have MA VA squared is going to equal MA VA prime squared plus MB, and then I'll put a parentheses here, times VB prime squared, which would be this whole thing. Quantity squared. And not to lose sight of our objective here, we're going to then solve this for VA prime. So notice this expression does not have VB prime in it anymore. It's all in terms of the masses, VA and VA prime. Okay, so let's do some algebra. Let's expand this squared piece. And I'm also going to just put everything on one side. So let me expand this and kind of consolidate the terms. We would have MA VA prime squared plus, notice what's going on with the MBs. We have MB divided by MB squared. So we would have just a factor of MB and then times this thing when we FOIL it out. So we would have MA VA squared minus MAVA times MAVA prime. We'll have two of those pieces, so we would have 2 MA squared VA VA prime. And then additionally, we would have plus MA squared VA prime squared. And then we'll also subtract our term from the other side, so we would have minus a factor of MA VA squared, and this thing would all equal 0. So I think you may see kind of where I'm going with this. We have terms that go like VA prime squared, a term that has a VA prime, and stuff that that doesn't contain VA prime. So let's reorganize this in terms of VA prime. So we would have VA prime squared. Consolidating all those terms, there's a MA, and then there's also a factor of MA squared over MB from inside this parentheses. And then in addition to that, we would have terms of order VA prime of order 1. So there's 1 inside of here, a factor of minus 2 MA squared VA over MB. And that's actually the only place where the terms of VA prime appear. And then everything else, we would have VA, well here, we just have the other stuff that we would have would be MA squared VA squared over MB minus MA VA squared. Okay, so notice why I have done this is because this thing is a quadratic. You have A, B, C. So you have an equation that's of the form, ax squared plus bx plus c equals 0. And to solve that, you're going to have to use the quadratic formula in one way or another. Negative b plus or minus c all over 2a. Now, unlike some of the quadratics that we encountered, for example, with projectile motion, etc., this is a little more complicated. We have a lot of pieces floating around in A, B, and C, so I would really recommend solving this on the computer. So, you can do this like on the computer, MATLAB, etc. You want to do it in a way that's efficient because it's easy to make mathematical errors with this, and that can be really frustrating when you have a complicated problem. So when we do that, when I solve this quadratic, I get that VA is either 4.8 or negative 1.6. And then this brings up the question, well, which root is the right one? And turns out that this 4.8 was what we had originally, so it's not that one. So this is what we're looking for. So what we've just found is that VA prime for this question is negative 1.6 meters per second. Based on the numbers that we had, in here we can scroll back up to our numbers. So our mass initial for A was 0.45 kilograms. For B, it was 0.9 kilograms. Our velocity initial for A was 4.8 meters per second, etc. And when we put those numbers into our expression and solve the quadratic, we find that VA prime is negative 1.6 meters per second. Now, we also want to know what VB prime is, but that's easy. We can, to get VB prime, remember our substitution from above that we made was that VB prime equals MA VA minus MA VA prime over MB. Well, now we know what VA prime is, so we can use that and substitute in for VA. So VB prime will equal MA VA minus MA VA prime, where now we know what this is, all over MB. So maybe with this one we can put in our numerical values, 0.45 times, what was that? 4.8 minus 0.45 times now negative 1.6, all divided by 0.9. And we would find that VB prime is equal to 3.2 meters per second. Okay, so we've solved this question. This was an elastic collision, so we conserved both energy and momentum. And you saw that it led to a system of two equations where we substituted one into the other, and we did some algebra, and then we had to solve a quadratic. So it was fairly complicated. So now I want to show you some tips, some tricks that you can use to solve this kind of problem. So let me show you a trick. Come on, pen. 1 second. So an aside, a tip for dealing with one-dimensional elastic collisions. And let me put this in a different color. This is only applicable to 1D elastic collisions, but it can really simplify things. So let's look at basically the general case of this. So in general, for 1D elastic, you have some MA, VA, MB, VB, and they're gonna, hit each other, and you would be left with, so just a cartoon. This will be MA, VA prime, and this will be MB, VB prime. So in general, for a elastic 1D collision, the kinetic energy expression would be 1/2 MA squared plus 1/2 MB VB squared is going to equal 1/2 MA VA prime squared plus 1/2 MB VB prime squared. And from momentum, you're going to have the fact that, from momentum, you're going to have the fact that MA VA plus MB VB is going to equal MA VA prime plus MB VB prime. So this is basically the general solution. So let's see if we can come up with something by looking at these general expressions. So basically we have two equations again. Notice again, like the factor of 1/2 drops out. So what we're going to do is, from this second equation, let's reorganize this a little bit so that I have MA and MB all on the same side. So in other words, if I put all the MA terms on this side, I would have MA VA minus VA prime is going to equal MB VB prime minus VB. So all I've done is subtract, put this over here and put this over there. And doing that, I get this expression. So let's call this one 3. Now, let's take and do the same thing, basically, with 1. So if I take expression 1 and put all the MA terms on one side, I would have MA times VA squared minus VA prime squared is going to equal MB times VB prime squared minus VB squared. Okay. Now recognize if you have these terms, these difference of square terms, you can expand those. So this would look like VA minus VA prime times VA plus VA prime. So notice when you FOIL that out, you'd have that term that you started with. Do that on both sides. Okay. Now, let's call this expression 4. Now what we're going to do is divide 4 by 3. Okay. So I'll do this in a different color. So if we divide 4 by 3, we're going to divide here a factor of MA VA minus VA prime. Okay. So, and this might seem like sort of a strange step in that, or like, are you supposed to be able to do that? Well, think of it this way. We took something that was like A equals B, and then we divided by C. And the fact that if you look at expression 3, this equality is telling you that these things are equal. So we can divide one side by the first term and the other side by the second term. And when we do that, notice that a bunch of this stuff is going to cancel out. Okay. And then what we're left with is a really concise expression that VA plus VA prime is equal to VB plus VB prime. Okay. So, and we can reorganize this if we want. We could say that VA minus VB equals VB prime minus VA prime. And this relationship can be very useful. And just to reiterate, this is only for 1D elastic collisions. So don't go trying to apply this to all problems. But if it happens to be a one-dimensional elastic collision, you can make use of this. And so let me show you what impact this has on our hockey puck problem that we just talked about. Okay, so basically I'll just show you how this lets you solve this problem in a different way. So remember, we had this situation. We had a puck whacking into another one, and we knew the masses, and we were trying to find VA prime and VB prime. Okay, so let's just restate our momentum conservation expression. We knew from in this question, actually let me, that MA VA was going to have to equal MA VA prime plus MB VB prime. So look what we can do here. This relationship that we just derived, VA minus VB equals VB prime minus VA. Well, we can notice VB was 0. So we can immediately come up with an expression for VB prime. Before we had that big thing that we substituted in. Well, here we can say VB prime is equal to VA minus VA prime. And we can substitute that in immediately. MA VA equals MA VA prime plus MB times VA minus VA prime. And then, we can solve that expression for VA prime. We've eliminated VB prime. So why don't we do that? MA VA. Notice we'll have a minus MB VA is going to equal VA prime well, yeah, let's factor it out. VA prime times MA minus MB. And then we can, solve for VA prime. Here we can factor out a VA times MA minus MB divided by MA plus MB. Oh, wait a second, I have a sign error here. Okay. And this was a much quicker way to get at VA prime rather than solving quadratic. And then, notice once you know VA prime, you can easily say, okay, well, we also know that VA equals VB prime minus VA prime. So if you know VA prime, then VB prime is easy. It's just VB prime is VA minus VA prime plus VA prime. So I wanted to show you this because it gives you another tool that you can use for 1D elastic collisions.